Thanks for being here. I'm honored to be able to present my work on the multi-objective optimization of a sustainable ternary mortar for 3D printing. So it's going to be more experimental work, sorry. I'm a PhD student and I'm supervised by Jean-François Caron from the Navier Laboratory in France and Claudiane Ouellet-Plamondon from ETS Montreal. So I'm going to introduce my subject in order to go to talk about the global objective of the study. I'm going to talk about the materials and methods and the optimization process, and I'm going to explain the results, have a little bit of the discussion, and conclude. So, as we all know, the cement production is responsible for up to 8% of global greenhouse gas emissions, and that's not even mentioning other impact categories or other concrete constituents. So, in that regard, the concrete 3D printing industry is already allowing a rise in productivity and a reduction in manual labor. But specifically for this study, the concrete 3D printing allows a reduction in material use. So as we can see on these figures from the French company X3, the concrete 3D printing benefits from the absence of formwork and the structural and topological optimization that it can provide. But if we look a little bit at different material compositions from the literature, and if we concentrate on 1K 3D printing systems, which rely on unaccelerated concrete, as opposed to 2K 3D printing system, which rely on a secondary mixing with accelerating admixture in the print head. If we look at these materials, that they have a pretty high cement content, and indeed due to rheological constraints of pumpability, shape retention, and buildability, the 3D printing concretes have pretty high cement content. And if we add the non-linear behavior of cementitious materials with increasing number of parameters such as admixtures and supplementary cementitious materials often used in 3D printing concrete, we have a rise in cement content and thus automatically a rise in global warming potential. So this study aims at proposing an automated reproducible methodology for the reduction of the environmental impact for 3D printing materials. And we are going to apply this to a mortar with very low cement content in this study. And we'll focus solely on the global warming potential. So we chose to apply this to a limestone calcined clay cement named LC3 because it has a greater cement substitution potential. And indeed, on this figure from Anthony and Al, we can see that the B45 mixture, which is an LC3 with 45% cement replacement, has a higher compressive strength at 28 days than the 100% OPC-based concrete. And we also want to demonstrate that the process is relevant for a higher number of parameters. So the materials used are cement general use with 8% silica fume, calcined clay with 80% metakaolin, limestone filler, sand with a maximum particle size of 2.5 millimeters, and PCE-based superplasticizer. So the transportation distances are indicated for the life cycle inventory. So in terms of methods, the physical characteristics are defined through rheological tests presented on the next slide. The printability, is defined with a literature review and actual large-scale 3D printing done at ETS. For the lifecycle assessment, we use an open-source software named Brightway 2, which is a Python package, along with its graphical interface activity browser, and the database Ecole Invent 3.7 cutoff. And finally, for the optimization, we use artificial neural networks and a non-dominated sorting genetic algorithm named NSGA2, which are also Python packages. So that's important. We optimize the material for a continuous mixing system with a pumping unit attached, and it's linked to a 6-axis industrial robot with a printing head. So in terms of printability, we have a range of rheological tests that cover the 3D printing time frame. So we use for flowability the flow table test at 2 minutes, and we set a threshold at 120% flow. For the shape retention, we use the slump test with a miniature Abrams cone at 8 minutes. So we set the criteria to approximately 65 millimeter slump. And finally, for the buildability, we use the direct shear test with circular shear boxes at 30 minutes and 60 minutes. And through a regression with the slump test result, we get a linear thixotropic structuration rate named ATIX. And so to sum up, this is the profile of a yield stress evolution that we want for a continuous mixing system. We have the competing objectives at the start of the mentioned flow and slump. And we set an arbitrary buildability criteria. We wanted a 0.5 meter elevation at 30 minutes and a 1 meter elevation at 60 minutes, which correspond to 6.2 kPa and 12.5 kPa respectively. So as I said, it's arbitrary. We used the following assumptions. So 2 meter contour length, 1 liter per minute flow rate, and a 69 millimeter per second tool center point speed. So that gives us an structuration rate of 3.5 pascals per second. For the life cycle inventory, we use the range of Quebec adapted processes and mixed processes based on the EcoInvent database. So particularly, we modeled the cement general use with silica fume, the limestone powder, and the calcined clay, and we associate them with the different other constituents of the concrete. We exclude the robotic system, the printing, the transportation phase, the use phase, and the end of life in order to conduct a cradle-to-gate study. So now for the fun part, the optimization process is based on a publication from Vassilis Sargis and Claudiane Ouellet-Plamondon published in Digital Discovery. So we rely on the collection of experimental data through a optimal design of experiments. So we use these experimental data to train artificial neural networks and along which I include a parameterized LCA model. And we use these predictions and this LCA calculation to as objective functions in the ranking of non-dominated solutions in the generative algorithm NSGA2. And so through selection, crossover, and mutation, we get a uniformly distributed set of Pareto optimal solutions, or at least a non-dominated front. So that means we get a set of best compromises between competing objective functions. And so the idea now in this study is to select a few of these solutions for validation, so for reproduction in the lab, and either for validation of the predictions or for progressive iterations of this process in order to get better predictions in the experimental regions. So we chose this kind of active learning process because of the high variability and in the materials that we get. And so the idea is not to have from the start a generalization of the models, but more through consecutive iterations, a better representation of the experimental region for specific objectives. So for the results, we base our design of experiments on a reference materials that we found from a trial and error process with more than 25 mixes, with the goal of lowering the global warming potential. So we have these properties which are considered printable, but the goal is now to lower the global warming potential while maintaining printability constraints with an automated process. So just for preliminary results concerning global warming potential, this is important because it will orient the study and orient the algorithm results. We plot the weight proportion of each mixed constituent against the climate change score proportion. And we observed that although accounting for as low as 7% and 6% of the weight proportion, the cement GU and the calcined clay CC account for more than 53% and 34% respectively of the global warming potential. And so the substantial impact of calcined clay can be attributed to kaolin production, kaolin calcination, and calcined clay transportation. So now for the results that we have, the dashed lines represent the normalized objectives for printability. So for flow and attics, we want a point that is on or above the dotted line. And for the slump, we want a point as close as possible to the dotted line. And at the bottom, you have the global warming potential reduction. So in red, you have the predicted results, and in green, you have the measured experimental results. So for the first iteration, you can see that the algorithm kind of captures the mixed design trends, but the errors are still are high, especially for the slump. For the second iteration, the algorithm explores unseen experimental data, unseen experimental regions, sorry. But for global warming potential reduction up to 13%, but the errors are still high. And for the third iteration, so that's 9 additional mixtures, we observed that the algorithm proposes 2 mixtures that approximately satisfy the printability constraints. And from these 2 mixtures, we can select the last one that proposes a 6% global warming potential reduction while satisfying all the printability constraints. So we can see that this is an effective way to reduce the global warming potential of complex materials, and we found a lower cement content mixture in as low as 9 additional mixes. And if we go one step further and expand the experimental region, so for even lower cement content region, we can see that in 2 additional iterations, so 6 mixes, we find another printable mix with even surprisingly good structuration rate, and with lower global warming potential. So if we can comment on these results, if we set no criteria for compressive strength, the algorithm always tries to minimize the cement content, but we can see that this does not affect the structuration rate that we have for a cement content as low as 100 kilogram per cubic meter. The algorithm then tries to optimize the calcined clay content since it has a substantial impact. Indeed, in the LCA model, we have a pretty conservative modeling of calcined clay. So we have a rotary kiln calcination with natural gas, an electricity mix from Saskatchewan, Canada, that relies 85% on fossil fuels for the production of kaolin, and a transportation distance of almost 3,000 kilometers from Saskatchewan to Quebec. And that makes a 658 kilogram of CO2 equivalent per ton estimation, which is pretty high compared to the literature that can go as low as 150, 200 kilogram of CO2 equivalent per ton. So that means our presented figures of a global warming potential could be even lower with other technologies of calcination or other electricity mixes. To be noted, the reference material that we found through trial and error is already effective in reducing the global warming potential. So the goal of this study was to see if we could reduce it even more in a kind of straightforward way. We restricted the parameter boundaries of the optimization after an initial iteration because the neural networks had too much trouble predicting too far from the design of experiments region. But now that the predictions are better in a lower cement content region, we are progressively extending the experimental region as it was done in the iterations 4 and 5. But overall, we can see that for 6-parameter optimization with 4 to 6 objective functions, we expected substantial errors in the first iterations, but we can see that in as low as 6 iterations, the predictions get better. So the key takeaways is that the methodology is an effective way of reducing the workload and the material resources needed for material optimization. And it's an effective way also to include the global warming potential criteria in the mixed design, which is pretty rare. It's reproducible with locally sourced materials and customizable objectives. So let's say we want to design a 2K 3D printing system material. We could concentrate on the flowability and the reactivity with accelerating admixtures. And now the next step is to include the compressive strength in the optimization in order to switch objective and identify a higher strength 3D printing mortar with minimized climate change score. And also maybe to include a physics-based model in the artificial neural networks in order to get better predictions after listening to other presentations. So here are the references, and if you have any questions, I'd be happy to answer them.